So, in the last lecture, we looked at Hensel's lemma, various versions of it. So, what it allows us to do is to start with a solution modulo p or a factorization of a polynomial modulo p and get a factorization in the local field itself. Right. So, what we do is whatever, if we start with a solution, we lift it to a solution modulo p squared, modulo p cubed, etc., and then take the limit, and this is allowed in a complete local field. Today we are going to look at applications of this thing. In particular, we are going to look at algebraic extensions of local fields and what they look like. Right. So, we got last time we also proved that if you have two number fields L over K and you take a prime small p of the bottom field and a prime above it capital P in the bigger field, then taking the completion of the bigger field gives an algebraic extension of a smaller field, right. But is there any other way of constructing algebraic extensions of local fields? Well, there isn't, and that is what we are going to prove today. So, here is a lemma. So, let L be K P of alpha be a finite algebraic extension of K sub P. Let f of x be the minimal polynomial, of alpha over K sub P if g of x in K P of x is monic and close enough. So, I am not going to say what close enough means, but it means that each coefficient of g is close enough to the corresponding coefficient of f is close enough to f of x, then there exists beta in L such that it is a root of g, and L is also equal to K P of beta, right. So, L was generated by alpha, but you can generate it by something else like this. Moreover, so this last point turns out to be easy. Once we prove all the other parts, g x is irreducible. Okay. So, as a corollary of this, so this is first part, as a corollary of this we get every finite algebraic extension of K P is of the form f sub p, or maybe let me just say the easier version first. Is contained in f sub p for some finite extension f of k and capital P dividing small p. Okay. So, this is pretty much what I said we want to do, right, except that I have not shown its equal, but that will come later. So, proof, right. Okay. So, now we want to work with Kp, this L is Kp alpha, right. Now, problem is that K p alpha does not have a valuation yet. Right. So, I can't really I cannot really just say that I start with alpha mod some maximal ideal of ring of integers of L and then work with that, right. So, what I am going to do instead is the following. So, f of x is in f of x is in K p of x. So, we are going to replace this with g 0 of x in OK of x such that g 0 of x is close enough. Again, I am not really going to make any of this quantitative, but just a qualitative statement, close enough to f of x, right. And now, we are in the setting of algebraic number fields, right. So, there we know how to define valuations, etc. So, what I am going to do is beta. So, let beta be a root of g 0 of x. So, what I am going to so I am going to fix such g 0, then I am going to fix such beta, and then n be some neighborhood of f such that some conditions hold, right. So, such that conditions of the previous lemma holds, and I am going to say that in a minute what that means for any beta and any g in this neighborhood. Okay, so, I am going to make all that thing rigorous, but in a minute. Right now, it is kind of just an idea of how to prove things. Okay. So, and then I can take f to be the splitting field of g 0 over k, right, and take p to be any prime of f dividing small p. And so, now what we can do is we can, so we get we can embed both k p alpha and k p beta in f sub p, and this has valuation, right. And so, this problem that we had now kind of disappears and we can apply the previous lemma. So, how do we do this rigorously? Okay. So, this is the idea, and so how do we do this? We do it as follows. Okay. So, first, I kind of said a few things which really do not make sense unless my alpha is in O sub p. So, we may assume alpha belongs to O sub p, that does not really change anything. Hence, f of x is in O sub p of x right. And so, given two polynomials, G1, G2, you define d of G1 comma G2 to be product over all xi of G1 prime of xi. And what is xi? Xi runs through roots of G2, through roots of G2 of x equal to 0. Okay. So, it is kind of a strange thing, you take product over all roots of G2 and you, of this thing the derivative of G1 evaluated at xi, right. So, what happens is that if G1 and if there is some root of G2 that's a root of G1 prime, then only then we get that this quantity is 0. So, for example, if G has no multiple roots, then d of G comma G is non-zero, right. Okay. So, d of f comma f is not 0, as f of x equal to 0 does not have multiple roots. Okay. So, in particular C, which is valuation of d of f comma f, by definition this is not 0. Okay. So, what I am going to do is I am going to do the following. So, let n be a neighborhood of f such that d of G1 comma G2 has valuation exactly equal to C for all G1 and G2 in N. Now, this is kind of a subtle point, right. You can always yeah. So, maybe I will explain this point. So, this point is a bit subtle. So, you can always take epsilon greater than 0 and take neighborhood n such that valuation of d of G1 comma G2 is less than C plus epsilon and it is bigger than C minus epsilon for all G1 and G2 in this neighborhood, right. But once epsilon becomes very small, the valuation only takes a discrete set of values. Valuation takes a discrete set of values, right. So, if epsilon is sufficiently small, is small enough, then valuation between C minus epsilon and C plus epsilon implies valuation is just C, right. So, for a non-zero element it kind of takes discrete set of values, right. The only limit point is 0 and C is not 0. So, for epsilon small enough this is what happens. So, a condition of equality on norm usually is not a open condition, but this is how you do it, and this is why it is kind of tedious to make close enough quantitative, but qualitatively it is easy to understand what close enough means. So, this is one of the things that is required for close enough. So, in particular every element of n is in OP of x, right. Otherwise, you would not have this condition when you take G1 to be f and G2 to be g for this element g. Now, we need further condition on g on n. So, now if required shrink n so that every coefficient of f minus g has valuation less than c squared, okay, strictly less than c square. Okay, so, now we are finally ready to take our g 0. So, finally, we can take our g 0. So, take g 0 to be an element in n intersected with O x. And why can we do that? I mean, maybe this intersection is just 0, this is just empty. So, why is this non-empty? Why is this non-empty? This is because O, I mean when I say O, I mean O sub k is dense in OP, right. All right. Now, because of being an ultrametric, if you take every coefficient of g minus g 0 is also strictly less than c squared, right. So, now take beta to be any root of g 0. So, what do I get? If I look at valuation of g beta, this is equal to valuation of g beta minus valuation of g 0 beta, because g 0 beta is 0, and so this thing is strictly less than c square. Right. Okay. So, if beta I is any root of g 0, then g prime of beta I satisfies that valuation is less than or equal to 1, because g prime of beta I is in. So, as this is in O sub p, right. Remember O sub p was, so p is a, so recall f is the splitting field of g 0 over k, and p is a prime of O f dividing small p. So, that is the notation in the line on previous slide. So, now if I look at d of g comma g 0, this is product over all beta i's, these are roots of g 0 of g prime of beta i's, right. And I know that valuation of this is equal to c, right. So, hence valuation of g prime of beta, this fixed root that we had, was greater than equal to c. Therefore, using the previous lemma from last lecture, the last lemma from previous lecture, we get each root beta I of G0 has a corresponding root unique root gamma I of G. Okay. So, therefore, each of these G's has exactly as many roots as G0. Each G in N has exactly as many roots as G0, including F, by the way, right. Okay. And so, we get so taking G equal to F, we get part 2 of the lemma, right, and using the fact that Kp beta is also contained in Kp of alpha, right. So, we get degree of G is greater than or equal to degree of Kp of beta over Kp, which is greater than or equal to degree of Kp of alpha over Kp, which is equal to degree of F, right. But these two are equal, right. So, degree of G equals degree of F because they are close enough, hence Kp beta is equal to Kp alpha, right. And because of these degrees, you also get that that G of x is irreducible. So, we have proved that any algebraic extension of a local field is obtained as a completion of some number field, right. So, this is very good, otherwise if we were studying local fields and if we did not have this result, we would not know which local fields are related to number fields and which are not. Okay. All right. So, let me end with what is called approximation theorem, and yeah. So, so that will finish our study of algebraic properties, algebraic/analytic properties of local fields, and then we can go back to studying arithmetic of these local fields. So, we will define various quantities, discriminant, ramification index, residue degree, etc. for local fields, and that will help us kind of calculate these objects for number fields. So, here is a theorem, this is called weak approximation. Okay. So, let V1 up to Vm be distinct places of K. So, they could be Archimedean places, they could be non-Archimedean places. Let alpha 1 up to alpha m be elements of K. Then for any epsilon greater than 0, we can find alpha in K such that valuation of alpha minus alpha I at the place Vi is strictly less than epsilon for all I between 1 and m. right. So, a remark if, or maybe remark slash exercise, if V1 up to Vm are non-Archimedean places, then this is simply Chinese remainder theorem. Okay. And if V1 up to Vm are Archimedean places, then this is simply that K is dense in product KVI, I going from 1 to m. This is one of the first things we proved in the course. And so, what weak approximation tells you is that we can put these two things together. Okay. And so, unsurprisingly, we need to use these two results to put these two things together, right. So, that is what the idea of the proof is. Image of K in product V Archimedean, KV is dense, right. This is what we proved. So, let us say V1 up to VR are Archimedean and VR plus 1 up to Vm are non-Archimedean. So, we renumber Vi's and alpha i's in this way. So, take beta in K such that valuation of beta minus alpha I is less than half epsilon for I between 1 and R. And what I do is I take m greater than 0 in Z such that m times alpha I minus beta belongs to OK for all I between R plus 1 and m. Okay. So, by Chinese remainder theorem, there exists gamma in OK such that valuation of gamma minus m times alpha I minus beta at Vi is less than half epsilon the Vi adic valuation of m. Okay. So, R plus 1 less than or equal to I less than or equal to m, right. And now, we have to just put these two things together, right. So, the way to put these two things together is you think about it a little bit what it should be, and it turns out that this is what it should be for n greater than 0 in Z. So, we want n such that something happens, and what is that? The valuation at Vi is bigger than 2 epsilon inverse valuation of gamma by m at Vi for 1 less than or equal to I less than or equal to R, and then the valuation of n minus 1 Vi is less than half epsilon valuation of m by gamma Vi for R plus 1 less than or equal to I less than or equal to m, right. So, what this is saying is that the Archimedean valuation of n is very large, and that is probably okay because you are putting n in the denominator, but n is also not divisible by any of these Vi's. So, the non-Archimedean valuation of n minus 1 is very small, which means that n minus 1 is highly divisible by VI's. So, as a finishing exercise, you should show that valuation of alpha I minus alpha at VI is less than epsilon for all I. Okay. So, it is just putting these two things together. You take the difference of this with alpha I and take two cases when I is Archimedean and when I is non-Archimedean, and that will do this exercise for you. It is very easy to deduce it from this. Okay, so we looked at application of Hensel's lemma and proved that any algebraic extension of a non-Archimedean local field is obtained as a completion of a number field at some prime. Okay, so next time we are going to introduce arithmetic invariants associated to these local fields, and so a lot of the invariants that for number fields that we want to calculate, they will become local computations. Thank you.